Okay, welcome to your trial session for Anytime Tuition. Now, it's completely up to you how you use this trial session. You may choose to kind of just skip through it and just get a general feel of what the session is like as a whole. Or what I would recommend is sitting down and doing the session as if it was a proper tuition session for you, okay? If you would like to do that, I just want to give you a second to go and grab some resources, okay? You will need a pen and paper to write some notes on. So if you're going to do the session fully, then pause the video now and just go and grab yourself a pen and paper if you haven't got one already, okay? But now let's jump into our session. Now, today's trial session is a chemistry session, and it's a chemistry session based on exothermic and endothermic reactions. Now, please don't worry if you don't know what these are, because the point of this session is to teach you what these are, okay? But I don't just want to jump straight in and tell you right off the bat. I always like to get you thinking first and foremost, okay? So the first activity I'm going to ask you to do, not right now, but in a second, wait for me to tell you when to pause, is to just get you to have a think. What is the difference between exothermic and endothermic reactions? Where have you heard of these terms before, maybe? There's a hint there. Think about those prefixes, exo or endo. Where have you heard those outside of chemistry? And maybe the pictures can help you too. So you don't have to pause for ages, just a minute or so, and write down any ideas you have, what you do remember about exothermic and endothermic reactions. But as I said, don't worry if that's not too much, all right? Pause the video now, have a think, jot some ideas down, and unpause when you're ready to find out. Okay, so hopefully we've had a chance to jot down any ideas we had and have a think about what the differences are. Now let's find out. Now, I'm going to ask you not to write any notes yet, just listen up for now. We'll get notes down afterwards. And I'm going to bring up these definitions and then I'm going to explain them on my whiteboard. So, an exothermic reaction is one where energy is given out to the surroundings, whereas an endothermic reaction is one where energy is taken in from the surroundings. Let me explain. If I jump over to my board, I'm just going to draw two circles. And I want you to imagine that these are like our reaction vessels. So this could be just a beaker that you're pouring some chemicals into, okay? Now, an exothermic reaction, we saw on the definition, was one where energy is given out from the reaction to the surroundings. So energy is given out from the reaction to the surroundings. Whereas an endothermic reaction is any reaction where energy is instead taken in from the surroundings to the reaction. So hopefully you can already tell these are pretty much opposites, and that's how I want you to be thinking about them, because that will really help, okay? This is an exothermic reaction, I'll label it up here, whereas this one is an endothermic reaction, okay? Now, before we write these down, I want to ask one quick follow-up question related to this. How will these affect the temperature of the surroundings? You don't need to pause the video or anything, but just have a think. How would an exothermic and an endothermic reaction affect the temperature of the surroundings? Just have a think about that question for a second. Is it going to make the temperature go up, or is it going to make the temperature go down? What do you think? Now, hopefully, what we realise is, let's start off with exo. If an exothermic reaction is letting energy out into the surroundings is gaining energy. And anytime something gains energy, that's going to cause the temperature to increase, right? So that is why I drew this in red. And you're going to see pretty much everything I say today about exothermic reactions drawn in red, because that makes you think of things getting hotter, right? So the temperature increases. Whereas in an endothermic reaction, the opposite is true. Energy is taken into the reaction from the surroundings. So that is going to cause the temperature of the surroundings, I'm using this letter T to show temperature, to go down, because energy is being taken into the reaction, so the surroundings are losing energy. And if something's losing energy, it's cooling down. So the temperature will decrease. Nice and simple, right? And that's why I drew it in blue, because that associates it with cold things, because it's losing energy. So here's our little summary. Already we've got quite a nice summary about the differences between exothermic and endothermic reactions. And I'm going to ask you in a second to get these notes down. When I do, I'd like you to give a nice subtitle, energy changes. I'd definitely like you to get all of the notes in colour down on this slide. And you may also choose to kind of draw these diagrams to go with it. I think diagrams are a really good way to kind of visualise what we're talking about in words here. Okay, but I'll leave that up to you. Pause the video now, get these notes down, and unpause when you're ready to move on. Okay, so hopefully we got those notes down. Now, it's all good knowing the differences between exothermic and endothermic reactions, but one of the most common mistakes I see is just getting them mixed up, not remembering which way round it is. So, before we go too far, I want to talk about this. I want to give you some good ways to remember which way round they are, which one's exo and which one's endo, because as I said, there's no point knowing the differences if we're going to get them mixed up. So again, you don't need to pause the video, but just have a think. Can you think of any good ways to remember which way round it is? Which one's exo and which one's endo? Just have a think. Maybe you can think about some other places where you've heard these prefixes, exo and endo. Okay, now maybe you came up with some of your own, which would be fantastic. But if not, here's some of mine. The first one, which I think is super useful, is the idea of thinking about an exoskeleton. Okay, now an exoskeleton is something that is on the outside of something's body, right? Think about a crab or a beetle. They have a hard exoskeleton. Their skeleton is outside of their body, okay? And that protects them, right? Now, the fact that exoskeleton means on the outside of the body links to the idea that energy is given out in exothermic reactions, okay? So exo means out, exoskeleton, outside of the body, exothermic, energy is given out. And if you can remember that, then endo is just the other way around, okay? You only need to remember one and then remember that endo is the opposite, okay? Here's another, and this one's a bit simpler, I suppose. Exo makes me think of exit. When you exit a room, you go out of the room. So again, this links to the idea of energy being given out in an exothermic reaction, okay? And these are just a couple of little study tips to help you remember which way round these go. And you may not feel like you need these, but I would advise to write at least one of these down, if not both, okay? But I'll leave it up to you. Pause the video now, get these study tips down, and unpause when you're ready to move on. Okay, so hopefully we've got these down. Now, let's move on. And I know we've only just started this session, but we're actually already ready to have a look at a quick exam question, okay? Now, I'm going to be a little bit mean here. I'm not going to give you any hints at all. I'm just going to chuck you in and see how you get on, okay? All I'm going to say is think carefully. It's very easy to get this question wrong, so think before you start writing, okay? I'm going to read the question to you and then I'm going to let you have a go. A reaction between two chemicals takes place in a beaker. During the reaction, the reading on the thermometer goes down. Is the reaction exothermic or endothermic? Explain your answer. Pause the video now, have a go at this question, and unpause when you're ready to look at the answer. Okay, so let's have a look at the answer to this question then. Now, I'm going to jump over me to explain this. A lot of people get this wrong. I'm going to actually tell you what a lot of people think that is wrong first, before I tell you the correct answer. A lot of people think, oh, if the temperature on the thermometer is going down, that must mean that energy is being lost from the reaction. So that makes them think of exothermic. However, if you thought that, you've missed the fact that the thermometer isn't part of the reaction. Although the thermometer may be in the beaker, as you can see in the picture, it's not reacting. The only thing that is part of the reaction are the chemicals within the reaction itself. So when we're looking at the thermometer, you need to see the thermometer as part of the surroundings, okay? And now when we think about it like that, we think, oh, okay, if the temperature on the thermometer is going down, that must mean that the thermometer is losing energy. And so that energy must be being taken from the thermometer and pulled into the reaction. So actually, the fact that the temperature is going down means that it's endothermic, okay? Because energy has been taken from the thermometer into the reaction. That's why the temperature of the thermometer goes down, okay? And that's why we tend to associate endothermic with cold, okay? I'll bring up this explanation in words here, and if you want to pause the video and make a correction, you're more than welcome to. So the way I've worded it here is said, it is endothermic because energy was taken into the reaction from the surroundings, e.g. from the thermometer, hence the temperature of the thermometer went down. And as I said, if you want to pause and get that down, you can, but otherwise, let's move on. Okay, so we know the differences between exothermic and endothermic reactions. We've looked at a couple of ways to remember which one's which, and we've even just applied it with a quick exam question. Now, I want to move on and to have a look at some examples of exothermic and endothermic reactions. And the way that we're going to do this is firstly, and I'd like you to do this at the same time as me, we're going to create a little table. We're going to have exothermic on one side, and we're going to have endothermic on the other. And all I'm going to do is one by one, I am going to bring up some examples of different types of reaction. And your job, and I'll give you a bit of thinking time, is going to be to decide whether you think it's exothermic or endothermic. And then we'll have a chat about it, and then we'll add it to our table. Once we've got the correct answer, we'll add it to our table. Okay? Hopefully that's all clear. And let's just get going. So the first one I'm going to have a look at is this, an ice pack. For example, I've just got this one out of the freezer. You can see it's still got ice on it. Is this an example of an exothermic or an endothermic reaction? Have a think just for 5-10 seconds. Decide which one do you think you're going to put it on. Now, hopefully, what you went for was endothermic, because if you put an ice pack on your arm, which I'm not going to do for too long because otherwise I'll get very cold, you lose energy, right? You get cold. You are part of the surroundings. This is your reaction. So it's like the thermometer again, but this case, you're the thermometer, right? Your energy is being taken into the ice pack. And if energy is being taken into our reaction or our ice pack, that fits with our description of endothermic, okay? So I'm going to put ice pack on our endothermic side, which again fits with the analogy of endothermic being associated with cold things, okay? Make sure you've added that as well. And let's have a look at another example. What about photosynthesis? Very, very important reaction in biology. And here is an example of my carnivorous plant that I have in my office. Unfortunately, it is not doing too well at the moment because it's approaching winter, but it's a plant nevertheless. And this is an example of a plant that would be photosynthesizing, right? So have a think. Do you think photosynthesis is exothermic or endothermic? Have a think. Think about what you already know about photosynthesis. And how does it fit with this? Let's have a look. It is endothermic because light is taken in to the plant to perform photosynthesis, right? Plants take light energy in to make photosynthesis happen. So if the plant is taking the energy in, that fits with our description of an endothermic reaction. And to be honest, we don't really need to say any more than that. So let's just add it on, okay? Hopefully that makes sense. And let's add on photosynthesis to our endothermic side of our table. And let's carry on. Let's have a look at our next one. What about combustion? I'm going to speed up a little bit now because hopefully we're starting to get the idea. Combustion. For example, if we are burning a fuel, like in this lighter, something is being combusted, it's being burnt. Is this going to be exothermic or endothermic? What do you think? Now, hopefully, what we have decided is exothermic, because in an exothermic reaction like combustion, clearly energy is being given out by the combustion. If I put my hand close to it, I can feel the heat from it because energy is being given out, and that's what's heating me up. So combustion is most definitely going to go over here. Add that to your table as well. Let's keep going. Next one. What about a hot pack or hand warmer? So for example, something like this, very similar to our ice pack, but I would put it in the microwave, it would heat it up, and if I've got a sore injury or something, I would put it on there to warm my muscles up. Would that be exothermic or endothermic? Hopefully, a lot of the things I said there made you think exothermic, because again, not only do we have the association with things being hot, but think about it logically. This lets energy out from the reaction into our bodies to heat us up, and therefore it must be exothermic. So I'm going to put heat pack or hand warmer on my exothermic side. Okay, now these four I think were all right, okay, but the next two are a little bit more difficult. So let's have a look at them. What about a neutralization reaction? Have a think. I haven't got an example for this one, unfortunately, but have a think. A neutralization reaction where we react an acid with a base to form salt and water. Do you think this is going to be exothermic or endothermic? Let's have a look. It is actually exothermic, okay? Now, firstly, let's add this, but I'm going to mark it with an asterisk, okay? I'm going to say neutralization reaction on my table, and you should be doing the same, but I would like you to mark it with a little star, because I think this one is harder to remember than the others, because it's not as obvious. So I like to mark it just so we know that's one of the harder ones to remember. Now, if you've ever done a neutralization reaction, when you react an acid with a base, you'll hopefully remember that it's quite a rigorous reaction, okay? There's quite a lot going on. There's kind of fizzing and bubbling, and that should make you think that energy is being released. And so if energy is being released, it must be exothermic, okay? So although that one's a little bit tricky, we can still explain it in the same way by just remembering that it's quite an active reaction. There's quite a lot going on, which implies energy is going to be given out, okay? Last one. And again, this one's a bit of a toughie. Think carefully with this one. It's easy to get this the wrong way round. Thermal decomposition, which is where, for example, let's just try and reenact this. Let's say this pen is my copper carbonate, which I'm trying to decompose into carbon dioxide and copper oxide, which you can see on the picture. And to do that, I put it over a Bunsen burner and I make it decompose. Is this thermal decomposition going to be exothermic or endothermic? Think carefully. Well, let's have a look. It is actually endothermic. Now, a lot of people get this mixed up because they see the word thermal and they see the Bunsen burner and they think, oh, that must be hot, so it must be exo. But you need to think carefully. Where is the reaction? The reaction is your copper oxide, which in this case is my pen. The thermal energy from the Bunsen burner is being taken into the reaction. It's being absorbed from the surroundings into the reaction to make it happen, to make this decomposition occur. And if energy is being taken in, that fits with endothermic, okay? So let's add this as our final one, okay? Thermal decomposition. But again, I would advise marking this with a little asterisk, just so you know, okay, that one's a little bit harder to remember. I need to think carefully. You'll always thank yourself for these little things when you look back at your notes in a few months' time, okay? But there we go. There are our 6 reaction examples for exothermic and endothermic. And there are, of course, more. I'm not going to go through every single one you ever need to know, but hopefully those discussions give you an idea of what you should be thinking about to work out whether it's exo or endo, okay? Let's move on then. Okay, so they were some examples of exothermic and endothermic reactions, but there's a fair question to say, well, why? Why are some reactions endothermic and some reactions exothermic? What's the difference between them? What causes energy to be released in exothermic reactions but taken in endothermic reactions? What's going on there? We want to dig into that a little bit, okay? And you can have a think whilst I'm talking about this. Why? Why are some reactions exothermic and some reactions endothermic? If you want to have a bit of a longer think about that and try and work it out for yourself, you're more than welcome to pause it. But let's break it down. And we're going to kind of break this down in chunks and then put it together at the end to explain this question, okay? So it might feel like we're going away from this question for a bit, but we're going to bring it back in soon, I promise, okay? Now, in order to study this, we are going to have a look at an example of a reaction. Nothing crazy, a fairly simple reaction between ethane, which is the hydrocarbon you can see on the left, which I've got a molymod of here, and chlorine, which you can see next to it, okay? Now, ethane is going to react with chlorine. And as you can see, if I go back to the slides, the reaction is relatively simple. Basically, one of the hydrogens gets pulled off and it gets replaced with one of the chlorines. However, I want to break this reaction down in a bit more detail, okay? We are going to view chemical reactions in two distinct steps. The first step that I want you to view in any chemical reaction is this. Now, please don't write this down yet. We're going to go through a couple of slides and then come back and write notes. So for now, just listen up. Any chemical reaction, I want you to see the first stage as being to break all of the bonds in the reactants. For example, if I jump over to my molymods, I'm going to do this for you now, okay? The first step is basically to break every single bond. So I'm going to break off this hydrogen, and I'm just going to put them in this box and show them to you after. So I'm breaking all of the bonds in my reactants and getting all of my atoms separate, like you can see on the diagram, okay? You have to bear with me for a second because it does take a minute. I'm going to break my chlorines too. So I've done my first step now, okay? I've broken all of the reactant bonds to get all of my atoms separate, as you can see in the diagram, okay? And again, don't write this down yet. We'll come back to this in a second. Then, what's the next step? That's not how we finish, is it? Well, then I want you to see the second step as being remaking all of the bonds in the products. And you can see this on the diagram here, but I'm also going to show you with my molymods. Now you'll have to bear with me a second because it does take me a minute to put all these back together, especially when my hand can't fit in the box, but we'll do my best, all right? So I'm going to put my carbons back together and I'm going to start putting my hydrogens back on. So I'm remaking all of the bonds in my products. And a lot of them are the same as the bonds in the reactants that were broken, but not all of them. Because notice, when I get up to 5 hydrogens, the final bond that I'm going to remake on this one is not going to be a carbon-hydrogen bond. Because remember, it's a different product. I'm now actually going to stick a chlorine on. So when I remake the bonds in the products, some of the bonds are going to be slightly different. And that is going to be very important when we move on, okay? So I've got this product, and then finally I just need to put back together my leftover hydrogen with my leftover chlorine. And now, just like you can see on the diagram, I have my products. My hydrogen and my chlorine have basically just swapped place, okay? Now, yes, I could have just pulled one off and put it back on, but I want you to see any chemical reaction in these two steps, okay? I want you to see that we need to break all of the reactant bonds and then remake all of the product bonds, okay? And you'll see why I'm talking about it in this way in a second, all right? For now, though, let's just take stock of what we've done and get a couple of these notes down, okay? I'm going to go back to the previous slide, and when I tell you to pause the video, I definitely want you to get this note in green down. I'll leave it up to you if you want to draw the diagram as well. You don't have to, but you might find it beneficial if you do, just so you can visualize this a bit better, okay? Pause the video now, get that note down, and unpause when you're ready to move on. Okay, let's now get this second note down. Let's go on to the other slide. Again, definitely get the note in green down. And if you want to get the diagram to visualize it a bit better, get that down as well. Pause the video now, get that down, and unpause when you're ready to move on. Okay, so We've seen how there are two steps to any chemical reaction. We firstly need to break all the bonds in the reactants, then we need to remake all the bonds in the products. Okay, but why are you telling me this? How does this link to exothermic and endothermic reactions? Well, let's have a think carefully. Let me just quickly reset my Molymods and get one of my hydrogens back onto here and get back to my reactants. Don't worry, I'm not going to do the whole thing again because I know it does take a minute, but I just want to go back to my reactants to give you a quick example, okay? The first step I said was that we need to break the bonds, okay? But what is required to break a chemical bond? You can kind of see me doing it here. When I break this bond, what is required? What do I need to put into the reaction to make this bond break? Maybe you can see, what am I putting in? Hopefully what we're realizing, the answer is energy. When I want to break a chemical bond, these bonds don't want to break. I need to make them break. I need to put my energy in to make these bonds break. So anytime I break a bond in the reactants, I'm putting energy in to make this happen. Now again, don't write this down yet. I'll let you write notes in a second, but just keep listening for now. Now, quick follow-up question on this. If energy is put in to the reaction to break the bonds, does that mean bond breaking would be exothermic or endothermic? Have a think about that. You don't need to pause the video, just have a think for 5-10 seconds. If we put energy into the reaction to break the bonds, is bond breaking exo or endothermic? Now, hopefully, we ended up with endothermic, because if we are putting energy into the reaction to break the bond, energy is being gained from the surroundings by the reaction. So energy is being gained, which is exactly what endothermic was. So that shows us that bond breaking is endothermic. So now you're starting to link this up to exothermic and endothermic. Now, before we write this down, let's just have a look at the flip side then. If bond breaking required energy to be put in, then bond making surely is the opposite. So whenever I remake a bond, the opposite is going to happen. Energy is going to be given out, right? So anytime I'm remaking the bonds in my products, I want you to imagine sparks flying off and energy being given out, because that is the opposite of breaking a bond. So energy is given out from the reaction when bonds are made. And I could ask the same follow-up question. Does that mean it would be exo or endothermic? Hopefully we realize if it gives energy out should make us think of exothermic. So bond making is an exothermic process. And we're nearly there. We've nearly got all the little bits and bobs we need to put all of this together. But first, let's get some notes down about this, okay? I'm going to go back to the previous slide and we'll do it in the same way as before, okay? Get both of the notes in colour down for me. I would probably do the green one first, then the blue one, and then we'll move on and do the same on the next slide, okay? Pause the video now, get these two notes down, and then unpause when you're ready to move on. Okay, so we've done that slide. Now let's do the same for this slide. Again, green note and then the red note, please. Pause the video now, get those notes down, and unpause when you're ready to put this together. Okay, so hopefully we've got that down, and now we've got all of the little pieces that we need to answer the original question, which was this. Let's take it back to here. The original question before we started all of this was why? Why are some reactions exothermic and some reactions endothermic? Why do some reactions release energy or some reactions take in energy? And I'm going to jump over to my board and explain this to you in a bit more detail, okay? Because we have all the bits that we need to process this. We said before that any chemical reaction occurs in two stages. Firstly, we need to break all of the bonds, which we have just said requires us to put energy in to the system. But imagine I knew how much energy it cost to break each bond. I could, in theory, add up all of the energies required to break all of the bonds in my reactants, including my chlorine, and then that would give me some total amount of energy. So let's say that total amount of energy comes to 2000 joules, okay? So I have to put 2000 joules of energy in to make the bonds in the reactants break. But then, you need to listen carefully here, when I remake the bonds in the products, that releases energy, doesn't it? We've just said that after we've broken them all, we need to remake all the bonds in the products. And I could do the same thing, right? I could add up all of the energy that's going to be released when I remake all of the bonds in the products. And you may be thinking, yeah, but surely you're just going to get the same number. Actually, you don't. Because remember, not all of the bonds that we remake are going to be the same. Remember, in the reaction, one of the hydrogens is replaced with a chlorine. And the fact that we've got a different bond being remade means that the amount of energy that we get out when we remake the bonds is going to be different from the energy we put in to break them in the first place. So if, for example, I were to add up all of the energy that gets given out when I remake all the bonds in my products, it might give me 2500 joules. And now we can start to put it together. This, and I know it's a made up example, but this example, we have more energy being given out when we remake the bonds in the products than we have taken in to to break the bonds in the reactants. And so overall, energy is going to be given out. The exothermic process is winning. And so overall, this would be an example of an exothermic reaction because more energy is given out when we remake all the bonds in the products than is taken in to break the bonds in the reactants in the first place. Now let's look at the flip side. What if instead, let's say we still had 2000 joules of energy required to break all the bonds in the reactants, but now, what if the energy we get out when we remake all the bonds in the products was less than that? What if it was only 1500 joules? Now we've got an example where more energy is taken in to break the bonds in the reactants than is given out when we remake the bonds in the products. And this discrepancy means that overall, energy is going to be taken in. The endothermic process wins here. And so this would overall be an endothermic reaction, okay? And that is why some reactions are exothermic and some reactions are endothermic, okay? That was a lot, and I appreciate that. So let's now summarize it in words, okay? I'm going to go back to my slides, and there is a lot here, but I'm going to read it to you, and then in a second, when I tell you to pause, I'm going to ask you to write these down, okay? But let's just read this first. If the energy required to break all the bonds in the reactants is greater than the energy released when the bonds in the products are remade, the energy will be taken in overall and we get an endothermic reaction. So this was our bottom example. If, however, the opposite is true and the energy required to break all the bonds in the reactants is less than the energy released when the bonds in the products are remade, overall energy will be given out and it will be exothermic, just like this example at the top. And I know it's quite a long explanation, but that answers our question, okay? That answers why some reactions are exo and some reactions are endo. And hopefully that makes sense, all right? Now, final note for today. Pause the video now, get these notes down, and unpause when you're ready to move on. Okay, so hopefully we managed to get those notes down. I know there was a lot there. But I promise you it's worth it, because this all consolidates it in our heads and helps us to understand what we've just been talking about, okay? But I'm going to leave it there. In terms of content, I'm going to leave it there. I'm not going to teach you anything more, because we've learned loads today. We've done absolutely loads. We learned not only what exothermic and endothermic reactions are, but we've learned how to remember which one's which, some examples of each of them. We did an exam question, and now we've started to dig into this more complex stuff, looking at why reactions are exothermic or endothermic in terms of breaking bonds and remaking bonds. Okay, now if you're interested, I just want to give you a little bit of a snippet as to where we would be going with this next. Okay, I know this is just a trial session, but I always like to give a bit of food for thought as to where we go next with this content. Okay, the next thing that we look at in the curriculum is basically starting to do some of these calculations properly. Okay, I made up these numbers, but we know, as you can see in the table, how much each of these bonds costs to break or is released when is remade. You can see those numbers in the table. That tells you exactly how much energy is required to break or remake a bond. Okay, and we can actually work out not just if it's exo or endo, but exactly how much energy would be given out or taken in using some calculations with the numbers in this table. Okay, so if you're interested, maybe you want to sign up to these tuition sessions and we can learn about that in the future. Okay, now the absolute final note from me, I just want to mention that I have also put together a consolidation quiz to test your understanding from this session. See how much of the knowledge that you need to have picked up has actually gone into our heads and which bits has slipped through the gaps, so that we can fill those gaps in and make sure that we've got everything we need. Okay, so if you want to do that, you can check the description of the video that you're watching right now, and you should see a link to a Google form which will take you to that quiz. Okay, now these consolidation quizzes come with every single session. Okay, so for Anytime Tuition, every single session that you will do will have one of these quizzes attached to it. Okay, so if you want to check that out and just see what it will look like, you can do that for me now. Okay, but I hope you have enjoyed today's session. And if you have and you would like to sign up for Anytime Tuition, please just drop an email to andrewharetuition@gmail.com and we can start that sign up process for you now. But I'll leave it there. You were fantastic, and I'll see you later. I wanted to just add this little section onto the end of the trial today to show you how you're actually going to receive your sessions on a weekly basis when you're signed up to Anytime Tuition. For the trial session, I just sent you a link for the recording. But on a normal week, when you receive your sessions, it's going to look like this. Anytime Tuition is set up on a Google Classroom, which is accessible via a web browser or even on a really nice application on your phone. Now, when you log in, it's going to look like this. This is a student view, so it's exactly what you'll see when you're signed up. You've got your 3 classes for all the sciences, and if we just click into, for example, chemistry, you can see what it's going to look like. Now, at the top here, you've got stream, classwork, and people. And if I click on classwork, this is where the work for each session is going to be posted. So this is an example of the trial session that you've just watched, and I'll show you what it looks like when you actually bring it up. You can see we're going to just have a nice description of all the things that are within this session, a top tip for what you need to focus on this session. You've got the video recording, you've got the PowerPoint for the session, and you've got the Google quiz to consolidate your understanding. You can even mark your work as done, so you can keep track of which assignments you've completed and which are left outstanding. Now, I'm just going to jump over to the physics classroom to show you what the stream is for. So the stream is exactly where you're going to go when you want to ask a question. So if you've got a question to ask and you want some advice, you just click on here and you can post your question and I'll get back to you as soon as I can. You may, as you can see here, even get students helping each other out. So you can see here an example of a student asking a question, another student commenting to help them out, and then me just confirming that what they've said is correct. And this is what a typical interaction will look like for Anytime Tuition. Hopefully that just explains how things are going to look like from your side when you're signed up. But if you've got any questions about this, of course, just pop me an email and I'll be more than happy to answer your questions there.